Hello and welcome to the lecture number 18 of Physics 401A. In lecture 16 and 17, we discussed the free oscillation, forced oscillation without any damping effect or any viscous effect, and damped oscillation without any external forcing. Okay. Now in this lecture, we will combine all the three. So that will be a discussion on damped oscillation with a forcing term. Okay. Now, before coming to that, let us just recapitulate that in the case of free oscillation, we only have omega 0, the single frequency, that's the natural frequency of the system. Then in case of a forced oscillation, we have omega 0 and gamma. Gamma was the frequency of the periodic force, and depending on whether omega 0 is equal to gamma or not equal to gamma, we had the case of resonance or non-resonance, right? Then for the damped oscillation without forcing, we had the interplay or the competition between omega 0 and lambda. If omega 0 is greater than lambda, then that was the underdamped case, or lambda is less than omega 0, underdamped case. So this is still an oscillatory motion but not periodic because the amplitude is exponentially decreasing with time. Okay, and if lambda is greater than omega 0, then we have overdamped case, and we have the solution is a superposition of two exponentially decreasing function. For the case where lambda is exactly equal to omega 0, if you remember, we had a slightly different type of solution. Then this is still an exponentially decaying function, but it's now modulated by a affine function, or the C1 plus C2 t type of function of time. Okay. So this is this case is known as the critically damped case. Okay, here for combining all the three effects, that means free oscillation, forced oscillation, the forcing and the viscous effect, we can write the net equation like x double dot plus 2 gamma x dot plus omega square x is equal to f by m cos gamma t. Okay. And for simplicity, here we just neglect any initial phase in the forcing term. That means cos gamma t plus delta, that delta we have ignored here. Now, this is a small exercise for you. Try to write down the Lagrangian in this case. Okay, because you know the Lagrangian of forced oscillation without any viscous effect, we wrote in the previous lecture, and we also wrote how to elegantly insert the the effect of a viscous force which is proportional to V for one dimensional Lagrangian. Okay, now remembering all the things, can you write a Lagrangian for this equation? Okay, whatever. Now we following the same methodology as before. Here we also search the solution solution just after converting this equation of motion in its complex form. That will be much more easier mathematically. And then finally we extract the real part, okay, for the physical solution. So in complex form we write z double dot plus 2 lambda z dot plus omega square z is equal to f by m e to the power I gamma t, where where x is equal to just real of z. Okay. As in the case without dissipation, we seek a solution of the form z is equal to b e to the power I gamma t, right? That was the case of non-resonant force oscillation. Okay, for the particular integral part. Okay, we can follow the same methodology here as well. And replacing the solution in the above equation, this equation, we finally get b times minus gamma square plus 2I lambda gamma plus omega square omega 0 square is equal to f by m. So finally b will be given by f by m, and in the denominator m is multiplied with minus gamma square plus omega 0 square plus 2I lambda gamma. Okay. Now we define B, so B is in general a complex quantity. We define B as a real amplitude B, small b times e to the power I delta. So this is the phase part. and delta is also real over here. Then we get tan delta will be simply equal to 2 lambda gamma by gamma square minus omega 0 square. This one you can check. Okay. And B will be simply equal to f by m root over omega 0 square minus gamma square whole square plus 4 lambda square gamma square. Okay. So this is an exercise for you. If B can be written in this form, then delta and B will be expressed in terms of gamma, lambda, omega 0, f, m as these two. Okay. This one and this one. Okay. Remember, there is a square root over here for B, and for the capital B there is no square root. Okay, so that is something to remember. Okay, now Z is equal to, then I am just replace the value of B over here by small b to the power I delta. So Z will be simply B times e to the power I gamma t plus delta. Okay, and then the required particular integral will be the real part of this Z. Okay, so which will simply be b cos gamma t plus delta. Okay, now the total general solution can then be written again the case without forcing plus the case and the particular integral for the forcing. Okay, now once again, if you remember that now the equation without any forcing is this part, so an equation for the a solution for this part is the solution which we just got for dissipate for damped oscillation without forcing, and we will just put the solution for the under damped case, because this is the only case where we have some oscillation. For the other two we just have exponential decay. Okay, so we just take an oscillatory solution, and that is the case where lambda was less than omega 0, and then we had the for the case without forcing we have this solution a e to the power minus lambda t cos omega t plus alpha, and the forcing part effect is coming through this term b cos gamma t plus delta. Okay, once again gamma is the frequency of the periodic force. Okay, now the first term decreases exponentially with time, and hence after sufficiently large time basically this term will prevail. Okay, so that's why this solution is known as the transient solution. Okay, now note that here B is equal to f by m root over omega 0 square minus gamma square whole square plus 4 lambda square gamma square, right? So this is so B should be replaced by this term, and now you can see that when omega 0 exactly equal to gamma, that is the resonance case for undamped force oscillation. Okay, here basically we can also call this it's also a resonance for damped force oscillation. No problem in calling that resonance here too, but the thing is that the solution is not blowing up any longer at resonance, because omega 0 is equal to gamma just makes the B is equal to f by m to gamma lambda. Okay, so for a given f, B is maximum, that you can just do by differentiating and writing the differential coefficient. First order differentiation is equal to 0 and the second order differentiation to make positive. You can see that this factor in the numerator is minimum. Okay, is minimum when gamma is equal to root over omega 0 square minus 2 lambda square, and when this is minimum then B is actually maximum. So the condition for B is a maximum, is gamma is equal to root over omega 0 square minus 2 lambda square. This is also a very elegant exercise you can do easily. Okay, now the question is that it's very good to see what happens at resonance now. can we also see or to study the motion near resonance where the dissipation is small? Okay, that means again gamma is equal to epsilon plus omega 0 and lambda very less than omega 0 or just less than omega 0. Can we do something? So that means that will be so this is a generalized resonance for case with dissipation, realistic case, and this will be a generalized case of bits, if you remember that, right? So just think about this, and I will try to come back to this problem through a tutorial. Okay, thank you very much.